All right, so this is the Portland Linux Unix group, assuming people didn't come into the wrong room. Has anybody not been here before? I didn't recognize you. And can you introduce yourself? Or
Ryan.
Okay, how'd you hear about it?
Through a colleague at work.
Sweet, awesome. Okay, who else? Let's go this guy first.
Google Portland
Nice.
And, yes?
I'm Joe. I was referred here from the OpenZFS developer.
Oh, nice, okay.
Michael's still watching.
Yes, apparently.
Cool.
Okay, so thank you for all coming, and we have a speaker this evening, which is awesome. I'm going to talk about these things here for a moment. We have a clinic coming up. Ian is not here, but I am not going to be here for this. So it's at Albina Branch Library. It's in this beautiful glass-walled room. So I'm going to be out of town that weekend, so Ian's going to be taking over for me. But the most essential consequence of that is I bring like 3 boxes of random things. I am not going to be bringing those 3 boxes of random things. So if you have something, make sure you're self-contained hardware-wise, because I'm not going to be there. We will have wired networking, hopefully, because I've got my little routery thing, and we can plug cables into that. And Ian will have that. So it's the usual time, 3rd Sunday of the month at 1 to 5. The second news item is we need speakers. So if anybody has a topic, this is the last person that I actually have like on the hook for speaking here.
And he might walk out.
He may be. I mean,
Wait, hold on. What did I sign up for?
I do have somebody's on the line nibbling, and hopefully they might have come tonight, but they're not here yet. But that's August. So we're missing somebody for July. So if anybody has any ideas, any willingness to stand up in front of a small group of friendly audience and talk about nerdy things that you're excited about, that's what we're looking for. The next item here is this is slightly unusual. This is not on the regular program. There's a little story behind this. We have this domain name pdxlinux.org. We've had that forever, and by we I mean actually our what the hell's the guy's name? Dave.
Or Michael.
Yeah, Dave. Dave has that registration, and he's like unresponsive to email, and he's, God bless him, getting older and older. And so I've been trying to maneuver that registration into some place that can carry it on into the future. That has not happened yet. A friend of mine
Where does he live?
in Corvallis,
Oh, that's right.
we could track him down, if necessary. Michael said the way to get his attention is to ask him about, his favorite kind of raspberry, because he grows fruit down there. Turns out there's this weird-ass domain name, the .or.us domains, and apparently this has been managed by this thing called PrairieNet for a long, long time, and they've all kind of fallen out of favor, and the guy who managed that domain has died 3 years ago. And a local guy just managed to this is all second, third hand, but I know the guy who got it, managed to social engineer his way into proving to the person who controlled the thing that he's actually a legitimate person and would do the nice thing. So he has delegated linux.pdx or Portland or .org.us to us. It's still kind of in transition because we're dependent on OSU OSL to slave the domain for us and serve, and they just haven't set up the slave stuff yet. So, but that might be coming, but it's always going to be a supplemental thing to the PDX Linux thing. So you don't have to learn anything new, but just for fun, we might have that domain name working. And then after this, the talk and questions and answers and all that stuff, we go to Patty's. Typically after this, which is down at First and Yamhill. And if anybody needs a ride down there, hang out afterwards and find somebody, and we'll probably be able to get you down there. So now we're about to start, and I just wanted to say I've known this person here, Jesse. Since I worked briefly at OHSU/CMOP, which I've talked about here before, Coastal Margin Observation Prediction. Jesse was a PhD student at the time and is now like a full-fledged PhD person, I assume.
That's what they say.
Yeah.
I got a paper at least that says so.
And he was super cool. And he was in the cubicle right across from me, and he was super friendly, and we talked a lot. And they did cool stuff with Linux machines and supercomputers and all sorts of cool stuff. So I will let him give his presentation.
Awesome, thank you. Thank you for the invite.
Yeah.
First of all, excited to be here. I've known about this group for a long time, but I've never actually made it. So when I remember when seniors, Russell, I called you by your last name, which is weird. When Russell told me he was involved, that piqued my interest, and that was like a decade ago. So it's taken me like a decade to actually make it here, which is maybe some insight into how much I procrastinate, I guess. I'm the opposite of fast. Here's the title, Inside AI Supercomputer. So I'll give you a brief overview about me. So I'm a AI ML architect and a technical program manager at Azure. So we run probably the largest fleet of AI supercomputers in the world. Actually, not probably, we do. So as Russell said, I'm a former computational scientist. I have a long background in HPC, so I've been using distributed computing and supercomputing for a long, long time. Also have a background in AI and ML before the two were married, which is very convenient for a career, given the state of the world that we're in. I've been a Linux user since the 1900s. An intern told me that, and I was just slack-jawed that they called it the 1900s, because that was just really, really strange. It made me feel very old. That that's how kids refer to the 20th century, where I would just say, since the 90s, and they're like, oh, that's a whole century ago. So I was like, I'm taking that one. I'm still in it.
ML.
Machine learning.
Machine learning, yeah.
And POC. What?
Second bottom line. Building POC telemetry.
Proof of concepts.
Oh, okay.
Yeah. So I'll get there. So I deploy infrastructure, so clusters for customers, help them run their workloads on these clusters. Then when you're managing and building out and deploying these clusters, there's a lot of operations that are involved, right? So it's like build out to customer workloads and all of the issues they see. So customers run into all kinds of problems when you're operating at scale. And sometimes the platform that we provide doesn't exactly meet their needs. And so that's where we develop like quick proof of concepts. So, bust out some bash scripts that do whatever they need done that our platform doesn't do for them, and stuff like that. A lot of times it's around like I/O, making the most use of the GPUs because they're incredibly expensive, right? So you don't want them to be laying idle. And then we generally feed these back into product improvements, and the idea is that in the future, all the customers benefit from these kinds of things. So just some notes about this talk. I'm going to really focus on like the infrastructure because it's like, the zeitgeist now, really. We see a lot of news articles and talk in the community, and I'm sure amongst family and friends, about data centers and the impacts that they are imposing on communities, right? So I won't speak too much about that. I think we all know about the issues involved. I'll tell you more about like what they're physically made of and the scale, and then you can infer like why they may have an impact on to various things like water and power. So I use these like as a sysadmin. I view them as computers, like a Linux box, that are massive, right? And then you see a picture of how big they are, and you're like, whoa, it's like a Amazon warehouse, kind of thing. So one thing, definitely, I'm glad somebody just asked questions right away. Please feel free to interrupt at any time. Definitely prefer going back and forth. So let's go. So, in the voice of Jan Brady, for folks from the 1900s, AI, right? It's just everywhere, right? So there's the languages, right? All the tools, the the agents. That's probably dominates like the use of the GPUs and so forth. But there's also like the images, right? You see all the AI slop images that are produced and pollute all over the place. There's video, which is kind of interesting to me, but also kind of sloppy. Like there's like runway AI, which is actually used in motion pictures for some frames now. There was Sora, but they kind of got rid of that Kling. Also like self-driving cars, right? All of that stuff is what we would call AI now, I guess. Recommendation system, these are all like using these compute clusters. And like everybody knows, right? Since ChatGPT, basically the thing has gone bonkers. And just a little brief story about that, personal story. Well, I first joined Microsoft in 2022 as part of this group before ChatGPT. And I went to the supercomputing conference 1 week before ChatGPT came out. And NVIDIA had totally cut their marketing budget, so nobody was going from NVIDIA to the supercomputing cluster conference. I was literally, as a Microsoft employee, at their booth because they wouldn't pay for employees to go. And then 1 week later, ChatGPT is released, and then the world just totally changed. And now you go to supercomputing, and the whole thing is all NVIDIA, NVIDIA, NVIDIA. And you know, Cerebrus and Grok and a little bit, but man, it's crazy how much the world has changed in my time here. So, question time. I'm very interested if anybody doesn't use anything. It doesn't use any AI tools.
It's define you. Define.
Any
Intentional or like it's part of a product you use?
either case. Because I know, like, I think some folks like just don't want to use it for like ethical purposes, perhaps, or environmental reasons or anything.
Well, I'm the person that uses a search engine, and the AI helps me give me something entirely not what I want.
Yeah.
Back when Google used to work, and it would use the words that you gave it.
Yeah. We all remember.
I will say I'm a super skeptic because I thought, hey, I'd try it out with something. This is all 6 months ago. With something I already kind of knew the answer to and see what I got. Not technical subjects, you know, sort of general knowledge kind of things. And it was total garbage then. I mean, it would eventually just tell you, ask somebody who knows. But I will say that just last night I was trying to type some find with horrible space embedded file names, you know, so -print 0xarg something. But I was trying to tar those files, and that didn't work because when you get the maximum line length or whatever the maximum args, it would just launch another one. And of course, it now was stomping on the same tarball. And I asked one of the chatbots, like, how can I make this work? And it actually gave me a real answer that I was able to use. So.
Yeah.
Yeah, I just a little over a month ago downloaded a local LLM. It's a Gemma 4, however you pronounce it. And I've made some good use of it, writing some short Python scripts, and I asked it if plutonium is safe for human consumption. It gave me a good answer, actually. It was really quite reasonable. Yeah, it just
Amazing.
runs on my desktop computer.
Nice.
Does it count if you post a question to the plug list and someone else?
Yes. That's my proxy. That counts.
Directly using it.
Yeah.
Get user support, and people will send errors in with like logs, and it works pretty well to break down what actually the error is and why they're experiencing it. So it's good for certain things.
Yeah, for sure. I think.
The user support, though, I do tech support, and the idea that it is not even close to being ready to actually provide support to another human being. It fails hard in that area. So every once in a while, I check against like a real conversation I would have had with a customer. It can't even come close to what competent, support technicians can do. But since we're shipping everything off to other countries and whatever, it does a very good job at imitating, just reboot, It
Yeah.
can't actually talk to someone about a problem they're having, because what people say with the sycophancy and the hallucination, it doesn't know how to tell that someone is giving information that is incorrect. So if you ask it a question, the onus is on you to make sure the question is correct. If the question is wrong, it's going to go very quickly down a weird path, because it just doesn't know how to be skeptical in a polite way and be like, okay, you didn't lie, you just didn't know how to answer. So before we start, let me make sure I collect all the information first. It can't do that. You have to do that for it. And from a support perspective, like a tech support chatbot, if it can't ask someone to provide more detail about
Yeah, absolutely.
That's a different thing than just generating code.
Yeah, I think these are some of the big use cases where I really felt, so like I would, instead of like building these long pipes, like step by step that, take whatever, 5 minutes or whatever to get exactly right, now I can just be like, I always have Claude Code sessions open and be like, do this. If it's above like a certain complexity level, and it just nails it, and it knows how to do it. And it just does it on its own now, right? So it is good for that. And for debugging, like I can have it just, like, there used to be this thing, Sawzall or Dremel from Google to go through log files, and it's just ridiculously good at just gathering boatloads of logs and finding connections and telling you like what the issue is.
Yeah, they're rolling in, I mean, my company is all into Microsoft Azure right now. So I log in at work at myapps.microsoft.com. So, and they're rolling out Copilot, and they're rolling out this AI text where we can ask if we stumped from the customer service. I do customer service for laboratory equipment.
Oh, cool.
And it's got issues compared to that I've got decades experience with, how the equipment works and what could go wrong. It still needs a lot more learning process and more tweaking, because sometimes it just goes out in a tangent. But I have to say, there's two things about the vibe coding, as the new term these days. I played with Claude, and it created a Python. So I wrote this interface with Dash, using the HTTP API to talk to things, set up the networking, and do the streaming and the recording as a remote control on the laptop. And I thought, well, I would like to have a nice GUI, so let's play with Claude. And it created a Python program that kind of sort of worked, but forced me to learn Python. But it wouldn't work on my stable Slackware stable, because that stable is still on 3.9. I didn't tell it. I didn't specify. My bad. I didn't specify which Python dialect to use. It did in 3.12, which is on current, which works. But I had to learn enough to figure out what pieces weren't working quite right. But I also said, well, let's do it in C. C seg faults, and I can't find out what the heck is doing wrong. It did some weird pointer thing. It can't even grab the IP address.
Huh.
So
Interesting.
it just
Yeah.
spits out.
It also messed up with, you wanted two components. You wanted the API, the web API
Yeah.
component in C, but you wanted a graphical GUI in WX widgets.
Yeah.
And you asked in C, but WX widgets is C++ only.
Yeah.
So it just gave you the C++ code.
Yeah, and that's one thing. My bad, 'cause
You wanted C, but here's C++.
I'm a Carnegie and Ritchie guy from way back, so I forgot to be specific. But I'm looking through the template it gave. So well, maybe I got enough pieces now here to figure it out, but I haven't done that yet. But it's a lot of hype. It's you make pretty pictures, you can ask it questions, but I don't think they're training it correctly. To say no, or to say I don't know.
Yep.
And at this point in my career, or what's left of it, I'm thinking of retiring next year, so right? I'm thinking, I've got books, and until they burn down the libraries, I'll get better information out of there. Until they figure out, and then of course you have the ethical issues like you mentioned, where you got to build these massive data centers to process everything. Which, as a computer gamer, I'm really upset that memory prices and NVMe prices and GPU prices.
They're crazy. They're crazy. I was
bananas. I mean, it's like,
every day I look and I'm
you
like,
look at
this is
60
crazy.
Gigabytes of RAM. It's like you want $900.
Yeah,
for this thing?
it's out of hand.
They're gonna run out of investors, and all of a sudden they won't be able to buy any more RAM.
Yeah.
Yeah.
So I'll kind of keep
Yeah.
this short so we can get back to the talk. But to answer your question of like people who haven't used AI yet, I'm starting to run to the point where people who don't know what AI is start to use AI for like GUI navigation, and then they dig themselves into some really big rabbit holes that you as a support person have to go back and be like, okay, this is how you undo everything that the AI told you to do. So I think, kind of to answer your question, it seems like everybody's using it, whether they know how it works or not,
Yeah.
or whether they understand the fact that LLMs just are trained to put pretty words together into
Yeah,
code.
it's
Something
not
that looks
really
good.
AI, right? It's not really AI
not
because it doesn't
really
think.
AI.
It's just a search algorithm with a lot of data that can look at connections.
Yeah.
I disagree. I
Yeah.
think they are actually general intelligences.
I don't know. Wow.
I mean, yeah.
Humans are barely the general
I,
intelligence.
I think like the LLM, we're maybe getting off the rails here. We hit our context limit here.
So,
No more tokens.
Yeah.
why did you not have an example like protein folding up as an example? Does that really not fit with?
Oh,
you're
you know what? It
thinking?
does. It is. I mean, there's actually lots of scientific. Actually, this morning I was in a call with somebody at Google that has hurricane forecasts. It's all AI driven, and it's much faster and more accurate than the standard legacy. I don't want to say legacy. The standard way of actually solving the partial differential equations. So they run it on a bunch of TPUs because they're at Google, and it runs like in a minute. Whereas if you're actually running the simulation, this like the closed form governing equation with like Navier-Stokes, it takes a really long time on a supercomputer, and this one you can just run it on like one node. So there's lots of science applications where it's being used, and math, right? There's always these new, like every day I feel like there's some new proofs coming with math because they're very good at logic, right? They can work through logic very well.
Yeah, the application comes to mind for me is FPGA layout, or placing. You've got a Verilog code. Now go figure out how to place and route it on that chip.
Yeah. So people, that's a real thing. People are using it now. I just randomly had a conversation with somebody who's like uses Verilog as their career, and they're like, it does all my work for me now. So very good at that kind of stuff.
One of the things I want to hear about in the talk is that I've always used this statement: if you get something for free, you're the product.
For sure.
And so they're not making money now. So I can't undo giving them, helping them build a model of me by the questions I ask. And is anybody thinking about the meta problem of what happens when their investors are saying we want to see some returns? So you're selling this information to the KGB or something like that, whatever you do to monetize it.
I think the history of the tech industry is that they will take your data and try to monetize it.
Right.
So.
I try to imagine AI monetizing me. Oh, he's this blood type. Oh, there's this billionaire who needs this organ.
It's getting a little topical because that's been coming up in the news in the last couple of weeks about the token prices. That's literally just starting to change.
Yep.
Where they're starting, people talk about charging more for tokens.
Yeah.
Giving a lot of it away. And the tokens are the monetization metric. The more tokens you have, the more you're spending. And the prices might be going up in the near future.
Anthropic's been ramping up token prices for well over a year, so for sure.
Yeah, I downloaded the whole thing I'm using for free and just pay for my own electricity. I think of it more like getting samples at Costco. They're giving out these models for you to play with. Say, hey, do you like this? Maybe you might want to buy a bigger one. But
And
kind of the philosophy I have.
What they're doing is they're trying it in a whole bunch of stores and they're doing, how much heroin do we need to put in this?
I would like to just have an aside about just what is token and in terms of what it means to a human.
Oh, we can do that right now. So apologies, I didn't. Well, it's kind of out of scope, but really quickly, a token is just like when you give text to an LLM, it has to somehow parse it. And the way they do it is they tokenize it. And so basically, there's a vocabulary that the LLM was trained on, and some words, some small words, are a single token. So like you is probably a single token. But larger words are composed of fragments, like togethers, maybe 2 or 3 tokens. And so the word together would be like 3 tokens. And so when you put text into the LLM, there's input tokens. So it takes your text, it tokenizes them, so it turns them into integers, and then those integers are then put into an embedding space. And then the output's the exact same way. You have some output is floating points, then they become integers in the tokenized vocabulary, and then it gets converted back into text.
Okay, well, you tried.
Yeah. All right. So this is what I'm going to cover. So basically, like why these clusters exist, right? What is the motivation? Why have we been scaling like crazy? For a while, for probably a decade really, but really ramped up recently. Then what's inside? What are the components, right? What's running on them? And then at the end, like how are the users actually using these enormous machines, right? So here it's NVIDIA marketing picture of their GB rack level GPUs there, the GB 200. So tell me if this sounds familiar. Who's used an HPC cluster before? I understand there's one here at Portland State, right? So what are some of the attributes of these clusters? What do they have?
Suck a lot of power.
Power,
Bunch of CPU
CPU, yeah. How do you connect to them?
over the network.
Network,
A lot
yeah.
of switches, a lot of managed switches.
Fabric connections.
There's a fabric, right? High-speed interconnect for east-west traffic.
It's all about parallel.
Yeah, login node, a head node, scheduler node, exactly. And then when you're on the head node and you run a job, what do? How do you do it? You submit a job, right?
Yep.
There's a scheduler, right? So Slurm, PBS, SunGrid Engine used to be there's a whole bunch of them. So you log into the
Batch
new.
process.
Yeah, right, exactly, like a timeshare, right? It's like the same ideas, right?
From
So,
the 1900s.
well, I mean, if you look at this picture, it kind of looks
Yeah.
old. So this is at CERN, actually. This is the CERN data center. This is the CERN, very tiny. I didn't realize it would be this small, but yeah, this is from CERN, actually. So this is just like a classic, like, HPC supercomputer, right? Compute site. So yeah, basically they have a scheduler, right? Whatever scheduler you have. Slurm's the popular one now since Livermore produced it, whatever it was, over a decade ago. Oh, geez, man, it's like 15, maybe over 15 years. Oh, it is more than 15. I'm getting old. The 1900s. The long end nodes, you're right, the head nodes, the compute nodes, you're going to have some fast, low latency interconnect, right, for these jobs. Parallel file system, you have a home directory, right, where your files are. It's usually on a parallel file system, NFS, Lustre, whatever, GPFS, right? So a lot of folks have experience with these kinds of things, right? And these have been going on. They're basically like Beowulf clusters, if everybody remembers that term from the 90s. I think maybe, there was a whole movement in the 90s about Beowulf, and then it became really popular. And this kind of displaced the old vector supercomputers that were all vector processors, like the old Crays and stuff. So it's basically a bunch of like commodity hardware, basically in racks, wired together with fast connections. So that's basically what like HPC supercomputers are. So what's an AI supercomputer? Basically, you take an HPC cluster. Instead of having like the nodes that an HPC cluster would have, you swap those out and you put in a GPU node that basically is focused on the GPUs. It's got a bunch of GPUs in it. And that's it. That's all it is. It's the same thing that we've been doing for decades. The nodes slightly change, right? And then of course, because you have GPUs, the power goes way up. And then there's some, different labs run different things. So some labs still use Slurm, but most labs use Kubernetes now. Maybe you don't have a parallel file system. If you have Slurm, you're going to have a parallel file system. But blob, accessing data from blob or object store is so fast now that on these huge clusters, they don't have a file system. They basically load data from blob to local NVMEs or straight to the GPU, because there's RDMA there can be RDMA from object store to the GPUs. So remote direct memory access, right? So you could just write remotely to the memory. It all runs Linux, right? All up and down, except at Azure, because our hypervisor is Windows. So ignore that part there. But everywhere else, it's all Linux. And then instead of MPI, typically we use Nickel or RICL for collective. So Nickel is the NVIDIA collective library, and it's super optimized for their fabric and the GPUs. RICL is the AMD version. Basically, like AMD has like very similar products to NVIDIA, and their verbs basically is like if it's Nickel, you just like change one letter and that's the AMD version. But they're basically the same, and you use them the exact same way. So that's basically it. Oh, yeah, of course. In traditional HPC, like on the cluster here, I noticed there's like GPU nodes that have 1 or 2 GPUs for the GPU nodes here. On the GPU nodes in a AI supercomputer, there's like 4 or 8, depending on the generation of the hardware. They have very fast connection in VLink for GPU to GPU connection, so it's actually a switch, and it's got super high bandwidth, and lots of HBM, lots of very fast memory. But still the bottleneck. So that's it, right? Thanks for coming to my TED Talk.
So a question
Yeah.
on scaling. I used to do some switch fabric, and I hired a bad marketing guy that didn't know how to sell it. Generally, I found that endpoints or switch points go up as the square of endpoints, more or less at a very large level. Now you've got more things talking to more things, and how does the scaling?
Yeah, the scaling law that I think of is actually to the cube. There's a cube involved somewhere there, which like definitely limits scaling.
Yeah, I was trying to tell my marketing, okay, you want me to do Ethernet chipsets. I want to do these things which are a whole bunch of optimized crossbar connect. And well, I didn't make my $1 billion off of that startup.
Should have went over here. Should have made that.
No, I mean,
Yeah.
This was
No, just kidding.
back when dinosaurs roamed the earth and dates had a 1 in front of the year.
In the 1900s.
Yeah, the 1900s. Yeah. So I mean, these switches aren't super big. Like on a node level, historically, like there's either 4 GPUs or 8 GPUs, right? And so that's the scaling of the. But now, I'll talk about it later. That's scaling up now, so the switches are getting much bigger. But we'll get to that.
You got to start worrying about silly little things like speed of light and.
Always a problem.
Kilowatts per giga.
Yeah. So yeah, the metrics we used to use in HPC was flop per joule, which is probably still the metric if you think about it, that's still used. It's just that you use a lot more joules per flop.
So what does the physical hardware look like?
I will show you.
Okay.
I will show you.
I assume
So,
this is not off the
here we
shelf
go.
anymore.
So here's an HPC supercomputer. So this is Frontier. This is the first exascale supercomputer that's at Oak Ridge. Took a long time to get here, but it's actually super energy efficient. When I was a grad student, I had a DOE fellowship and worked on like supercomputers and HPC stuff. And at the time, they were saying like what were the Intel chips around at the time? It was Haswell. Haswell was probably the most power efficient one. And they said basically you need a gigawatt to get to an exaflop in like 2012, 13, 14, around that age. So this was earlier this decade, and it's 20 megawatts, so way better, right, than the gigawatt we would have needed a decade before. So it's a lot more power efficient. And then this is Amazon Center. So this is Project Rainier, which was built for Anthropic. And if you look at them, you can kind of see why NVIDIA calls it an AI factory. Because if you look at it, it just kind of look like it's very industrial, right? It's like kind of a factory, and these are just flop machines, right? Doing matrix multiplication over and over again, so Claude can write crappy C code that doesn't actually work because you didn't tell it to use K and R, right? So
Now, way back in time, those big clusters were designed to replace bright glows underground where you're testing your weapons without actually testing your weapons.
that is definitely the origin, for sure. Also, weather forecasting or climate work.
Right.
Climate work comes out of the same thing.
I mean, and nuclear winter, but.
Yeah. No, that's exactly right.
What I'm wondering about, and you probably would have to shoot me if you told me the answer is, I mean, you can weaponize AI in terms of screwing people up, but you might also find some interesting new physics that allows you to build a megaton weapon for $1.98.
It's a powerful tool. I mean, the sciences are actively using it. Probably, I'd imagine for every good actor, there's maybe some bad actors around, for sure. Just like any powerful tool. I think that's true.
Yeah, when I gave a lecture once at Lawrence Livermore, and they said their motto was, if we don't do our job exactly right, millions of people will live.
Looks like the size of it is limited by the width of the wire going into it. It's all wire.
Yeah. a lot of power, right? A lot of copper.
So those are power cables coming down?
I actually don't know exactly. I assume there is lots of
Yeah.
power and interconnect.
Looks like it's the bigger one on the end, like that pink
I think
one
this
there.
could be
That's
part of the
probably
cooling.
Yeah.
Some of that's water.
Yeah, I think I think these are probably cooling units adjacent to the rack.
I was
Oh,
at a
yeah,
data
yeah.
center, I worked at one that had power attachments that looked very similar to that.
Yeah,
where there was
the-
a big thing coming down
the-
the ceiling.
The whip, that's what they call them, whips.
Yes, yeah.
You kind of already answered my question, but yeah, it was basically like, you know, you mentioned that like AI supercomputers are basically just supercomputers with just a bunch of GPU nodes. Are they just using just off-the-shelf like consumer like GPUs, or are they using like specialized like data center like?
They're data center GPUs for sure. Yeah. And I'll talk a little bit about those, but they generally they're not consumer. About a decade ago, NVIDIA kind of split. So back in the day when there was what we used to call GPUs, so general purpose computing with GPUs, they were just gamer cards. And scientists or computational scientists were hacking them to do gem for science, right? So they'd go and get a gamer card, put them in their box, and they were making some real. And then NVIDIA released CUDA, and it took off from there. And then at some point they said we need to make data center class GPUs instead of having data centers filled with like.
LEDs.
Yeah, exactly. Who put a mechanical keyboard here?
When you have to leave the server open because the cards they bought have the wrong angle for the power connector.
Oh yeah, exactly, right.
So
They're
all
off the back.
motherboards and stuff like that, it's all custom and stuff.
Yeah. So they'll build them custom for this like site, or like NVIDIA has specs for each generation, and all the vendors basically build it to spec, and so they'll all be the same.
It's boring.
So I've got a quick question.
Yeah.
Why are the lights on?
You got to have text to go and replace DIMMs and
Yeah, I
all
suppose.
that.
So do you ever see any of this hardware?
I have not gone into. I've been in DOE supercomputers, but I haven't been into like an Azure one. Periodically there are like field trips, but
Yeah.
I've never been around when there is one. Yeah. There's a data center up in Washington. Periodically we have data. Although, yeah, maybe go knock on the Google's door out in the Dells and see if they'll let you in.
And they'll put you to work and you'll never get out.
Yeah.
Well, the NVIDIA boards are proprietary, AMD boards, and I think the Intel ones comply to the compute project standard.
Oh yeah, I didn't know. I did. Good to know. Makes sense for AMD to do that because they need to get any kind of leverage as possible to kind of break out of that CUDA mode. All right, so I'm just going to kind of explain like why these exist. So like, first of all, like why GPUs? It's because like machine learning is all matrix multiplication. These algorithms just use GEM, so generalized matrix multiplication, matmul, over and over again.
This is actually integer times integer.
Floats, they're floats.
Or 4 bits.
Yeah,
12 bits.
it's generally floats. So, and it's not full precision. So, coming from science, I was like, always using double precision, and you don't need precision, right? Like, there's all kinds of like super low precision, and the precision's going lower and lower. So, like the latest hardware is using FP4, which is crazy to me, but it works. These
You can sell all
algorithms
those
don't need
old
it.
Pentiums that didn't work.
Yeah, exactly.
So FP4, that's like 4-bit.
Yeah.
16-bit floating point.
But,
16 integer.
I
So-
can do that with nonlinear analog circuit, that would be faster.
try it. You got a market. There's a big market, right? So all of these GPUs are just like all the algorithms are just doing GEM. So you want to do GEM as fast as possible. That's basically it, right? And the reason is like CPUs, they're good. They're optimized for latency. GPUs are throughput, and the throughput is just going through the roof. I should have actually just ran some samples to show you how much the difference in GEM between like a CPU and a GPU. I'll do that homework and send it over on the list or something, because it's crazy how much faster it is. It's good to have some numbers in here. So as I mentioned, so AlexNet was probably the big neural network breakthrough. That's when, so image was like an unsolved problem until about 2012, when this guy used neural networks to solve ImageNet. ImageNet was this kind of data training set to just recognize whatever the object was in the data set, right? And the way it worked before is that people would build all these super specified classifiers like edge detectors and shades and face detection and all this stuff, and they'd build up all these kernels in a cascade to try to detect what kind of image thing it was. So there's like these expert system kind of things. Didn't work really well. Then some grad students, I think they were at, where were they? I think they were in Montreal, but they used 2 GPUs. They wrote a neural network, worked really well, worked fast, and then neural nets took off from there. So that was kind of it. And then the gem was like taking off, and NVIDIA starts adding this hardware, like supporting matrix multiplication in the actual hardware. And then now we get matrix multiply and accumulate intrinsics. So 1 clock cycle to do an entire matrix multiplication and an addition and a clock in FP16, BF16, and FP8 on the newest hardware. So the trend is lower precision, bigger like systolic arrays to do tensor operations in a clock cycle. So training, I'll touch a little bit on what the training that goes on. So basically, the way it works for training is this is the loop. You get a batch of training data, you do a forward step, so this is like inference. You get some predictions, you compare the predictions to what they actually should be, the ground truth, you get some kind of loss, and then you run an optimizer on the loss that does gradient descent, and then you just go in a loop.
And how do you test the ground truth?
The ground truth, you have to give you make the ground truth. You provide it to the algorithm.
If I'm always in trouble.
Yeah. Well, so this is the great thing about LLMs, just briefly, it's like before you used to have pairs, right? So like ImageNet, you'd like show it a picture of a cat, and it'd have to know, oh, this is a cat, that's the label, right? But when you get to LLMs, there's no labels. You just throw the text in there, and it learns from the text. So there's no label. So having labeled data set was actually a huge bottleneck for a long time in machine learning, because you needed this labeled data set for it to learn. Now we don't have that problem anymore. We can just throw data at it, and it learns on its own, which is kind of incredible. So on a single GPU, if we're going to train like a small model, like the size that you were running, the Gemini model you were running on, like a similar size Llama, if you're going to run on 1 GPU, an H100, which is still like a workhorse GPU, but is a few years old, it would take on a small, not a huge size of tokens or a huge data set, 207 days, right? Nobody's going to wait around 207 days because maybe you didn't give it a good data set. You get the results, it doesn't work well. So, right, clearly you want to speed things up, right? That's not going to work. And also, like, you're super limited in the size of the model you can support in a single GPU, because even just like a 7B model takes up like 60 to 75 gigabytes. There's all this quantization tricks you can do and offload from the GPU to like system memory and stuff, but it makes it super slow. But generally, so if you want to keep it in the actual HBM, you're kind of limited in the model size. And if you want to use the bigger models that go up to like, hundreds of billions of dense models, like there's no way that's going to fit in a single GPU, right? So there's 2 motivations to go to distributed training. One is like speed faster and bigger models, right? But there's also another thing going on. It was a thing called the bitter lesson. I don't know if folks have heard this before, but this is a strong scaling motivation. So basically the bitter lesson in AI was that, just like I said before with like ImageNet, people used to make all these embed all kinds of domain knowledge from experts into the models. But the bitter lesson is that just giving the models more compute and more data works better. And so it's always bitter because you're like, the domain experts are always getting just outdone by more data and more compute. So it's led to this kind of flywheel of, you scale compute, you get bigger models because you have more compute available, then you get better results, and then you scale the compute again because you're like, oh, we'll get more GPUs, right? Then we get bigger models, more data, bigger models, and it just keeps going. And this has been going on for LLM since the Transformer paper was written in 2017. So we're like still just going around and around and around, and this is what's kind of driving this, is this bitter lesson, right? But there's a question, right? So if you're training a model, how much data do you need? And researchers came up with these scaling laws. The most famous one was called probably the Chinchilla paper. So a researcher at DeepMind wrote this paper, and he kind of did this work to figure out like the optimum number of tokens or the amount of data you need for a certain size of a model is this. Basically, he said 20 tokens, right? Yeah, 20 tokens per parameter. So that gave him a number to shoot for. Like we need this much data per model parameter, right? And so they would shoot for that, and that's kind of that guided them to determine how much data they needed. This led to people trying to download the entire internet, basically, right? So, because people are like, we're going to make bigger models and we're going to download more data, and then we're getting a bit more and more. So there was a point a couple of years ago where people were like, oh, we're running out of data. Where are we going to get this data? And so people are like coming up with synthetic data to train the models. Well, it turns out that like actually this is an underestimate. Just using 20 tokens per parameter is a little low. Generally, people use a lot more. So the different papers like Palm and Llama. Palm was from Google and Llama was from Meta. And
What is a parameter?
Oh, a parameter it's just it's a weight in a model. So if you just think of like a linear model, just y equals mx plus b, that kind of parameter. You have like in that linear model, there's one parameter, right? In these models, you have billions of parameters, but it's basically doing the same thing.
In those models, the m is just a tensor.
Yeah, that's it. They're just multi.
Ask what a tensor was?
Multi-dimensional
A matrix, an array.
Matrix? Or
Yeah.
Okay.
Yeah, n-dimensional array. Yeah. So this is so we have scaling laws, the bitter lesson, right? So there's this motivation to get bigger and bigger all the time.
I guess I should ask, what's Gopher in that context? Because outperform Gopher. Chinchilla outperform Gopher.
There was this micro trend of how they were naming the models for a while. I don't remember all of them now. So yeah, thank you. Gopher was just another model. I don't know. There was squirrel, chinchilla, gopher. Not yet. And wasn't there a Gopher protocol or something like that at some point?
Was there?
University of
I wrote a
Minnesota.
Gopher server.
Oh, no way! That's cool.
Didn't use AI.
No, it screwed up. It never heard of that.
Haven't we gotten some scrapers hitting it?
Oh, yeah, people have been scraping it. I think someone's, someone's, when the IP address,
Now I'm gonna go home
trying
and-
to get training data.
I'm gonna go see if I can make one when I go home. Go ask Claude to see if it knows about it.
But the
I bet it
protocol
does.
is really simple. It just
Yeah.
only takes a handful of lines of code.
Okay, so the scaling, right? That's motivating people to go bigger and bigger. So that's part of the motivation for distributed training, right? Train bigger, train models faster, and basically what you do. There's 3 basic ways to do this. Is you basically break up the model, right? So just think of the model as a bunch of parameters, these big arrays or matrices with a bunch of variables, and you either duplicate the model on GPUs and send data to each GPU. So that's an easy way to do it. That was very popular in even for training images. You would put a model on each GPU, and you'd send it different data. And then at the end of the forward pass, you average all the gradients, or in the backwards pass, you average the gradients and you update that way. There's tensor parallel, where you actually break up the tensors or the matrices, and you just split them up between all the GPUs. And then there's pipeline parallel, just like pipelining on a CPU. You break up there's a bunch of matrix multiplications. You could think of them as a pipeline of matrix multiplications. You just break them up and spread them out across the GPU, and you schedule it. So this is basically it. This is like the exact same kind of things you do on HPC. Basically, it's just applied to a different kind of data structure.
They use all of them, or which one?
All of
do
them.
they use?
They use all of them. Yeah, so they actually, there's even more. There's context parallel about how you separate the tokens and you shard the tokens basically. And there's also mixture of experts. So you have a problem and you try to break it up as much as possible, right, to get the scaling. That's the general idea. So just to show you like how much scaling can help in an idealized case. So on a 7B model that I was talking about, it would take about 207 days, right, on a single GPU. And then if you just like do a linear scaling and assume no GPU breaks or you don't have any InfiniBand link flaps, run it on 512 and it's only 10 hours, right? So that this is really what's driving people to scale up and do these hero runs where they're using a boatload of GPUs to train the model. because that's a huge difference in the time. And then so here's a real one. So Llama 3, 405 billion parameters, 15 trillion tokens, and they use 16K H100s, and they trained it for 54 days. 419 hardware operations. So some of the, back in the day, labs are very secretive now about this, because they're kind of a cutthroat competition. But they used to publicly, publish the training logs, and you would see like all the errors they would have. They'd be like 215, got pager duty, IB link flap, brought the job down, took an hour to bring it back up. DIM went bad, right? Like XID error on one of the GPUs, and you would see like all the issues that people have to keep these things up and running, so you can get it done as soon as
How
possible.
recoverable are they?
Totally recoverable, yeah. And there's a lot of work into make it super resilient, because, well, imagine if you're using 16,000 GPUs for a job, right? And it's tightly coupled, so they're all lockstep, and it goes down. That means you have 16,000 GPUs wasting. Yeah, and that's not cheap. So a lot of resiliency work. Here's just a look at this over scale, like where we've come. So BERT was an early model. I think it was an encoder, so there, well, that's an aside, but it was an early transformer model. I think that was from DeepMind, and then some early, so you can see they're like 3.3 billion tokens, which was huge then. I remember reading this and I was like, holy smokes, 3.3 billion parameters. That's huge, right? Because I always think in terms of DOFs in like solving linear systems. I'm like, that's massive. That's a massive system. But through time, as we've scaled up, we're all the trillions. We're using trillions and trillions of tokens, and parameters are like the big labs. Like they don't tell us like how big their models actually are anymore. It's assumed they're at least 1 trillion parameters. They're probably a mixture of experts, at least 1 trillion parameters. They're just massive, right? But they're not telling us. And training probably takes forever, right? That's why they have these enormous clusters, and they just keep them busy all the time. So what's inside of a cluster, right? So we've had this scaling thing. We know the motivation. What's inside? So there's GPUs. So here's a Blackwell, a GB200 actual tray or card. So on this die, this is a single board. There's the top 4 are the GPUs. So that's 4 B200 GPUs, and these are 2 Grace ARM CPUs. So it's got a
Who's
total.
the vendor on the ARM part?
NVIDIA.
Oh, okay.
Yeah, NVIDIA makes ARM CPUs. So it's all on the single board, and it has coherent memory. So there's interesting side effects about that, because when folks were first using this platform and they would load a model onto the GPUs and they would get an out of memory, usually you would get an error in CUDA. It would say out of memory, job would crash, right? And then you're like, oh, okay, I gotta make some adjustments so I'm not using so much memory. But because I had this uniform memory thing, the memory would spill from the GPUs to the CPU, and it was way slower than going over NVLink, and so you'd get all these weird performance issues and hits, and people were basically treating that as a bug. So in that model, initially, the OS was managing the GPU memory and the CPU memory, and it would treat the memory in the GPUs as a NUMA domain, which is kind of interesting. But now they've changed it, and the CUDA driver basically manages the memory of the GPUs, and there's just like two NUMA domains, the 2 chips. So just an interesting sidebar. But the things that are useful here is like they've got tensor cores, right, to do the matrix multiplication, the matmul and MMA, the matrix multiplication and accumulate. The CUDA cores, right, those are the things that are doing all the floating point operations. It's got memory. There's always an L2 cache in the CUDA architecture between the SMs, or the streaming multiprocessors, and the HBM. The NVLink is the switch I talked about that has a lot of bandwidth. It should be BDIR, that's a typo, bidirectional. And there's the design. So you can see here's the trends in the D types or the precision. So they started, you know, it was crazy. I thought it was kind of crazy when they added FP16 matrix multiply, again, because I was used to doing double precision all the time for science. So they're like, 16, what the heck? And then they did brain float 16, and then FP8, and now we're down on Blackwell to
So
FP4.
what is FP4 then? What's the?
It's a 4-bit floating point.
Like one bit
So what-
exponent and 3 mantissa or something like that?
There's a couple ways you can do it, yeah.
Yeah, only a few ways.
Yeah.
There's 16 or something.
Yeah.
So what's,
It's crazy, right? You're like, how's that even work?
what's BF16?
Brain float. So it's just they move around the number of bits that are used for the mantissa and the exponent. They just like shift it around. It was better at some time for preventing like underflow and stuff like that.
And this, you know, this is interesting. In the 1900s, I worked on.
Say it like that.
I introduced it because
Yeah,
an
yeah.
intern told me that.
I was working on stuff that used block scale floating point, and it's just the idea that there's 4 bits is enough to do anything useful.
I had the same reaction. I'll always go back to, I was a double precision guy, right?
Yeah, it's the way neural nets work. The precision is almost your enemy in a way.
It's all stored in vectors, so it's really just pointing a direction.
Yeah.
Yeah, in super high dimensional space, what is the, you know, I can't even, my brain can't even comprehend what it really means, right? So yeah, right, it's just like a
Less important
impulse.
to get to the exact right place. It's important to get in the right direction.
Yeah,
Okay.
yeah. Is it a direction? Yeah, I don't know how to think about this, like an impulse. But well, yes, but
So do we know what the numbers, so there's 16 numbers? Do we know what they are?
I mean, you can, I've never looked in detail about it. I just know it works. I guess I can go print them out, right? You can, I'll mail them to you. Because it's not going to be a huge manuscript, right?
Yeah, so what is the range, I guess? I mean, this is the.
Oh, yeah, I honestly,
All right,
I have no idea.
Ask the
Homework for
Oracle.
everyone.
Well, ask AI.
There you go.
It depends on how much exponent, how much mantissa.
Yeah,
just how
and I know there was at least two specific kinds that folks were advocating for, and I don't remember the
And
details
are
because
they signed?
I don't know.
So MXFP4 is assigned E2M1. So it's 2-bit exponent, 1-bit mantissa, and signed.
Yeah. Okay. There you go.
Okay, so it's just basically
So,
Like you said,
a
like a
scale or a
yeah.
number of magnitude.
yeah,
Yeah.
well, you've got,
yeah, like
uh,
impulse. Yeah.
But it's the combination of them in a block, in a tensor, like a multidimensional matrix that really points in some direction.
Yeah. Right. Billions of them, trillions of them. Right. Yeah.
plus 6 to minus 6, right?
Is that it? Yeah.
I mean,
Yeah.
2 bits.
Well,
if
yeah,
you
two.
think about having
Two.
3 of them, you can point in 3 dimensions.
Oh, fair
in
enough.
all
Yeah.
different ways.
Right.
And
Oh.
we're dealing with a lot more than 3 dimensions, but we can picture 3 dimensions in our head.
That's right.
Yeah, because it's matrix multiplication, you know, the advantage of like AVX vector instructions is you can pack a lot more into that 256 or 512-bit matrix. If these things were natively operating 64-bit, if
Yeah.
they're 2-bit, by shrinking it to 4 bits, you can now put 8 or 16 times as many vectors into that same computation.
It's like a big SIMD sort of.
Well, the warp. So I don't know if I talk about it at all, but the primitive is a warp on the GPU. So it's 32 threads, and those are basically SIMD operations on 32 threads. So you break up the workload into 32 threads called warps, and those are it's like SIMD units operating, and every single one's doing that. But you need the hardware to support it, right? Because back in the day, like before Blackwell, there was no FP8 support. So people would do tricks to basically pack them in to the larger sizes, and then they said, oh, there's something here, we should actually support that.
So
Nature invented this thing called a neuron that kind of works like that. Not very much precision, but a whole bunch of them.
Yeah.
And so you end up inventing Einstein's theory of relativity, and you end up bidding the stuff you see on Fox News.
So the word warp, do you know the origin of that?
I don't.
I
No.
wonder if they're pulling that from knitting, you know?
Yeah,
Like on a loom.
like weaving, like you have all
Yeah.
these threads and they're
Oh.
all
Yeah.
Oh, that makes sense. That makes sense. AMD calls them a wave.
Wavefront.
Yeah, wavefront. That's right. A wavefront. Yeah. So here's a node. This is what they look like from the glamour shots NVIDIA media posting, not a real one. Basically, so this is how H100, a Hopper or Ampere node looks like. So there's 8 GPUs, NV switch. It'll have 2 nodes. It has this generation had Intel's. Previous one had AMD in some of them. It's got 8 NICs, or they're really HCAs. So well, it depends on what you have. If you have Bluefield for Rocky or InfiniBand, you'll have HCAs. And so basically each GPU has its own HCA or NIC. And that's because you need to communicate quickly. And there's a ton of NVMEs on here. I think these nodes have.
HCA?
It's just what you call basically the InfiniBand
Okay,
network
yeah,
adapter.
yeah.
I even forget what it calls. I should know it, but
Communicate,
yeah. So these have 28 terabytes of NVMe on them. So because people load up a lot of data on the nodes and use it for training. Key things, so that there are PCIe versions of these GPUs, but they're quite a bit slower because the memory bandwidth is just so much slower, right? They're limited by the PCIe. It's only 128 gigabytes per second, but if you use the NVLink version with the SMX, it's 900 gigs. And huge difference in benchmarks with that, especially if you're doing tensor parallelism. Anything that requires lots of communication between GPUs on a single node, you definitely want to go with the NVLink and the switches. So this one has 8 GPUs. And it's crazy, right? The GPU is super thin, right? And then you have these massive heat sinks that are just enormous on top. But the newer ones, they're a lot thinner, the trays. I think they're 2U, and they're water cooled, and there's only 4 GPUs. Right? It's the chip I showed before. So this is the new one. Those are slotted into what we now call trays, and 4 GPUs per tray. The older ones with the Intel chips, they have 8.
Oh, hang on. The board, that board and the next picture are the same thing?
No.
Just with the heat sinks, or
No.
there some-
Different generations. This is H100, and this is GB 200. So this is the ARM and
Okay,
newer.
but they're equivalent. This just doesn't have the heats. They're not the same, but
They're similar, right? Yeah. So
Yeah.
underneath the heat sinks, there's something like this,
Okay,
basically.
all right,
Yeah, that's
all
right.
right.
Yeah. There's a
and then
board.
these plug in to. I
Yeah,
guess you're
where's their
getting
interface?
there.
They'll plug into this, something like this. It's just there's no heat
Like
sinks.
an edge connection?
Oh yeah. There's a
Yeah,
backplane.
yeah,
So you plug it into a backplane,
Right,
and there's a bus bar.
right.
Yep.
Yeah, I was gonna ask, NVLink, is that supposed to be the successor to NVIDIA's SLI connection, or?
Oh, I don't even remember. I remember SLI, but I don't remember.
For
Yeah,
To connect multiple GPUs, right? In consumer, I think that's what we used to use when we had old PCI gamer cards when I was trying to port PDE solvers to CUDA. Yeah.
So to answer that question,
Yeah.
essentially yes. So you can get the quote unquote PCIe versions of, so for example, the V100s, right, which is the 2017 Volta
Yep, Volta.
ones, right? They came in the PCIe version as well. So you can get a PCIe version, and they have the little slot on top.
Okay,
And
gotcha.
you can essentially jack in an NVLink. It essentially looks like a inverse PCIe.
Right.
And then you just jack it in and then you get NVLink. It is
That's right.
not, and that, if I remember correctly, is only that, I don't know if that's the generational NVLink issue or if it's that physical thing. It was only at 300 gigabytes per second.
Okay.
There is SMX on the Volta. I remember, sorry. So,
They changed it in 2018. That's when they started using NVLink as the interconnect.
oh, there you go.
So it is the continuation.
Yep.
In SLI, you had one primary GPU.
Yep.
And then, yeah.
That's right.
master
Yep.
slave or primary follower.
Yep.
Whereas NVLink is a pure peer-to-peer.
Pure switch. Yep. Yep, that's right.
And
You're
that's why
bringing back these memories of GPU systems I haven't thought about in a long time.
And then if you think back further, there's the original SLI with 3DFX, where it's literally just scanline interlacing.
And with SLI, so therefore you can only do 2, right? With NVLink, obviously you can do, like, I didn't
8.
even know this.
There's 8.
No, it might be the opposite. NVLink
Well,
is like
there's more, yeah.
Now,
Yep.
an assumption that underlies all of this is that the power company is going to be providing you power continuously. And you now get something from your input feed saying, power's going down in about 100 milliseconds. Store what you're doing and be ready to restart. Is that even conceivable with this kind of technology?
Yes. So there's SLAs about the power, for sure.
Yeah, but
Basically, it doesn't go down.
Yeah, so the power goes down. Okay.
But the thing is that you would, sorry,
Google's data power center engineers are giving talks about this and how
Yeah.
they're doing effectively like spot compute for GPUs.
Yeah.
Yep.
And you can do that geographically as well, right? So it's like, because there are constraints associated, like, right, like when you're doing these kind of SLAs, let's say ERCOT, for example, the Texas power, what's called, sorry, this is gonna get.
Admin,
Regional
government,
power
yeah.
Power
it's-
network.
It's
Yeah.
called an ISO, basically the regional service, anyway. So they will say things like, okay, for this particular hub, we have, let's say, 40 hours per year that we're power constrained. So we need you to have an agreement that you can set up this data center here with a gigawatt of whatever, but when we tell you,
You have
within
to
that,
shed load.
those 40 hours, you gotta shed the load.
Yep.
Yeah, I'm talking about, in real life,
Yeah.
a circuit breaker blows and your
Oh.
power is going
That's
Well,
not a
yeah,
that's not a
they have
concern
generators.
because you have
Yeah.
things like genset,
They have
to
generators,
battery to,
yeah.
and like nowadays you're going to 800 volt, so you essentially have multiple buses that, anyway, yeah.
Yeah.
Can you go back to the previous?
Yep.
just- I know you gotta move forward. Where is the power supply? I mean, how is power fed into this thing? Because this thing's gotta be sucking enormous
can you
amount of
tell on there?
power. And yet,
Yeah,
I
you
don't
can
see
really-
any power.
There's connection, 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 connection,
Oh,
connection,
okay.
connection,
Wow.
connection, 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 connection.
Okay.
And those are physical
Those-
connectors?
Yeah,
Oh,
Those,
it's a
so
pain,
that's,
yeah.
those are bus
Yeah.
power.
yeah.
I'm not sure about this specifically, but like if you look at, for example, again, the Volta series, which is the thing that I know of, so apologies if I'm giving old information. They essentially had, like, it was like 250 watts per GPU. So you're jacking in, so for example, the IBM's, what is it, the AC97 server series, it was enough, you could do like that 8 or whatever in like the 2200 watt. It was pretty simple, but again, it was just it jacks into those small little bus things.
Yep.
Do you know what voltage is going to the board?
I don't, yeah.
I mean, it doesn't.
Volta
look
is the
like
last one personally have ever put together, and it's fallen out of my brain.
I went and looked up the NVLink thing, so it looks like NVLink is what replaced SLI, but NVLink is just peer-to-peer, so it's one card to another card, and then the NV
Switch, yeah, the switch is in the middle.
It builds off of it.
Yep,
You have multiple
that's right.
connections.
Yeah, so, yeah, I have a picture of that, but that's right. There's a literal switch there, right, and links peer-to-peer.
Yeah.
here we go.
There. And there's the generations, right? So this is where we are now, right? So it just blows the PCIe out of the way. But it's a big on a single node. It's the bottleneck, right, for the tensor parallelism. So getting that bandwidth is important. And I'm just telling you, like the SMM form, that's different than the PCIe, where the GPUs plug into the base plate. Yeah, exactly what you looked up. I like it. Like, folks are super interested, right? I want to know exactly how it works. So that's cool. And then, so that's how the NV switch and the NV link is how you connect on the node. And then between nodes, we have the same fabric, right? So on an HPC cluster, you have InfiniBand. On Azure, we still run InfiniBand. And so this is what it looks like. The thing that's interesting about the the fabric now, the InfiniBand fabric, is called rail optimized, where so let's say you have 8 GPUs on a node. All of the GPU zeros from like in a rack will connect to one switch. And then all of the GPU ones in a rack will connect to one switch. And then they go up a level. And once you get to the core, that's actually when you get cross-rail communication. So there's this thing called adaptive routing in IB, and that does lots of interesting tricks to optimize the bandwidth and minimize traffic. And it will like route packets like up one switch and then through another node and then through NV switch and then up. And it does all these cool tricks. So it's super optimizing and just kind of mind-blowing about how it works. An interesting thing is that this, I think the rail optimized stuff, I don't think, it came from Meta, and they found that it was actually a better way to lay out the network. So if you go back 2 generations to Ampere, the A100s, they didn't have this rail optimized. They had just like standard, like all the nodes in a rack went up to like a leaf switch in IB and with all the rails, and there was a lot of congestion, and they said, hey, maybe we can do something about that. So here's just a comparison. So not everybody uses IB. Folks use Rocky. They use Ethernet and Bluefield instead. So the bandwidth's the same. Latency is much better in InfiniBand.
What's ROC?
Yeah. It's converged Ethernet. Okay. So RDMA over converged Ethernet.
Gotcha.
Yeah, so you can still use the RDMA verbs. Right. It's just using Ethernet instead of InfiniBand. Right. And there's a lot of overhead with InfiniBand. They have like a UF.
Nanoseconds?
Yeah, nanoseconds. So there's more overhead, more management, costs more. But if you want or need the lower latency, that's what folks go for.
The second is a foot of wire. You can get a lot of stuff on a foot of wire.
Yes, you can. And so just for folks that don't know about RDMA, it just allows you to bypass like the CPU and the kernel. So you can just go device to device from memory to memory. And it's super useful, of course, for something like this, or even like loading data from storage. If you have RDMA from storage, you can go straight from, like if you have your parallel file system that's hooked up to InfiniBand, you can do RDMA from like the Lustre to the nodes or something, right? So it can be helpful. So clearly, a big problem is there's like this bandwidth cliff, right? The big bandwidth cliff. So on node, on like Hopper, you got 900 gigs on the node, but then as soon as you need to go to another one, you get a big drop because each IB connection is only 50 gigs, right? So you have a total of 400, so it's basically cut in half. So this was like kind of a problem, especially for like, well, lots of different workloads, right? So this was recognized as like, lots of work was done into optimizing the algorithms and the communication and the collectives to like get around this, right? So you can always address the algorithms to do this. But the other approach is basically make the whole rack an NV link domain. And what they've basically done is made the whole rack an NV switch. So now with the Blackwell and NV Link 22, there's 18 trays, so 18 nodes in there. And when you plug them in, they're basically connected to a switch, and they're all basically act as one unit. And so every single 72 GPUs in there have the same NV Link bandwidth. And so that basically, you don't get rid of the bandwidth cliff, right? Once you have to go off node and you have to go over Rocky or InfiniBand, but within the rack, you've got a lot more GPUs that can access the super fast bandwidth.
They're not, in the previous one you said that NDR, like, they're not using NDR still, right, for InfiniBand? Because it's something like what, XDR and?
XDR is in GB300. NDR is on H series, so all the Hopper, and the GB200. So even the first version of of this guy used NDR.
Because I have like NDR at home. There's no way there's still, that seems absurd.
Yeah, there's still racks being built today and delivered today that have it.
That seems very old. Okay.
Yep.
It is what it is.
Let's see, anything else I want to say? So this is the domain we're in now, right? You're doing rack level deployments of GPUs. And AMD is doing similar things.
So your last sentence, optical NVLink removes the 7M copper constraint.
Meter.
Yeah, 7 meter.
What's magic about 7
Basically,
meters?
speed of light,
Yeah.
power, degradation stuff.
So it's not
Basically,
the
it allows them to put 2 of these racks together in the same switch with the same domain. So the next version, called Vera Rubin, is going to have 144 of these connected together. And that's just because the interconnects have improved. So just a comparison, right? So of H100 versus GB200. So that's the plain chip that I showed, what's called a Bianca board. The plain board without the heat sinks. That's this guy, and then this is the whole rack, and then this is like the previous generation, the one I showed you with the heat sinks. Those are the specs about it. So I mean, this is the scaling up on like every component as we've gone through the years, right? The GPU memory goes up, the CPUs go up. That's like super less important, but the memory bandwidth goes up, the memory available, the HBM bandwidth goes up, and of course, the power kind of goes up as well. Now, because if you notice, like those trays, they're only 2U, right? So there's no way you can put a heatsink in there. So these are all require liquid cooling. Kind of goes with the territory. You can imagine if the heat sinks were already, they're not that big. They're, I think, about this big is how big those heat sinks are. So you can imagine if that's like a 700 watts. So if you're already this big on 700 watts and you have to go up to 1,000, you're like, oh, it's gonna, it's a pretty big heat sink, man.
What is the fluid they use? Is it just water, or are they using?
Yeah, no, I don't know.
It's supposed to be a
Inert?
You can imagine.
Yeah.
Yeah.
some sort of oil, if I remember correctly, that don't go.
Molten salt.
Well, you get a salt reactor too.
The water has a whole lot of more specific heat than an oil, and you can do things to water so that it doesn't.
Yeah.
I think you run
You
into
gotta let it
like
evaporate.
cavitation issues though, right? Like when you're pumping it on that, at that heat, you run into cavitation issues.
That is, I've heard that at least in early versions, that was an issue for sure.
And then that can cause like pitting and such
Yep.
on your copper heat sink.
Yep.
Exchange, so.
Yep.
So it's usually a water glycol mixture
Mm.
or some sort of dielectric.
Mm. So just kind of walking through, so we went GPUs to nodes, now we're at racks, and then the next is, of course, clusters. You get a whole bunch of racks, put them in a data hall, and you get an enormous cluster. And the thing that makes them a whole cluster is they're all connected with the same fabric, right? So the same IB fabric or Rocky fabric, and they're all connected. And they're all managed like with Slurm or Kubernetes, and then folks, use these other frameworks like Ray or PyTorch or VLLM for serving, et cetera. It all runs on Linux, like I mentioned before. Mostly uses CUDA or ROCm if you're using AMD. See anything else? Yeah, that's basically it, right? So when you look at it, it's like you're like, oh yeah, if I just didn't have the GPUs, I mean, it's a Slurm cluster, right? Basically, I mean, it is a Slurm cluster.
So the GPUs themselves are running Linux?
Well, the nodes run Linux, right? Yeah. So just some real clusters and sizes, like the public clusters. Like Meta's got a big old H100 cluster that they're public. There's this super infamous one built by an infamous guy. This announced project with Microsoft and OAI and Stargate. It's quite, so they're here, and they say they're going to get here, and then supposedly somehow magically end up over here.
They have the power for it. That's impossible.
Yeah.
A miracle.
Yeah. So this is the picture I showed you, the Project Rainier. That was the one I showed you. That's an Amazon cluster for Anthropic. Google's got a ton of TPUs. They're spinning up all over the place these days. And they also do run NVIDIA hardware as well. And then Oak Ridge was the other picture that I showed. And of course, like, yeah,
That's
yeah.
not for Franco's underground.
But remember what I said, if they tried to build that back when I was in grad school, they said it would have taken a gigawatt basically a decade earlier. So the energy efficiency has improved a lot. But yeah, still, it's crazy. It's an order less than the GPU clusters.
For what it's worth, Amazon is now claiming that they have over 1 million Trainium chips in Project Rainier.
Yeah, I wouldn't doubt it.
I heard an interesting quote that in the UK, there are enough, say, data center projects pending or submitted that would use, for the next year, that would use 8 times the existing power of the entire island.
This is fine.
Yeah.
And
Yeah.
Well, I like warm beer.
I don't, and I ran, in fact, someone on a building science, like home performance forum, said he works on data centers, and yet he says all this power is being generated, but as he's worked on this, and the only thing he can do with the heat is make sure that the ice doesn't build up in the winter on the parking lot. I mean, you would think you could do
the heat.
You could pipe it.
think you could do district heating or something like that.
In Finland, they do.
Yeah.
Yeah, in Finland, they actually do. They use it
With
for
the with
Yep.
the data center?
Yeah, with some.
Okay.
There are multiple, there's a northern German town that has, there's like a large enough data center. It's definitely not, it's in that, like the 20-ish megawatt range, right?
Okay.
But the big thing is you take the heat that you get, and then you can kind of quote unquote multiply it with a heat pump system, right?
Yeah.
So
Okay.
it's not that,
Well-
then you run into like the issue of like, voltage versus amperage,
Sure.
right? It's like, you don't-
I think in this case, the guy, it didn't pencil out financially, that he couldn't figure out a way to leverage that heat to make it worthwhile in his situation.
Yeah.
But he did, but the parking lot is clear.
I bet you this is the issue in UK side, right? Like they're still using methane for a lot of house heating, for a lot of district heating, et cetera, et cetera. I bet you now that methane is so expensive, especially since it gets shipped, now it'll pencil out.
Yeah.
Well,
Yeah.
except the methane has got to go to the generator.
And a reminder.
That make gigawatts for that.
Just back to this guy, just as a reminder.
Yeah.
Okay, so one thing I didn't mention, right? We were talking about compute. Got to have some storage, right? Where you have your data from. So I think in traditionally we had like NFS servers like Lustre, whatever, OrangeFS, BHFS. There's a million of them, GPFS. Some folks still use it for sure, especially like as I mentioned, the folks who run Slurm clusters, they'll have a parallel file system like ANF. It's common in Azure for home directories for IOPS reasons, and Lustre for data. But there's other newer stuff like Weka or Vast Data. A lot of the neoclouds use Vast. Basically, they have disaggregated storage solutions where they utilize all the NVMe available on the nodes and create a coherent like layer above that. So if you have 28 terabytes of NVMe on each node, right, you can come up with some creative uses of that for sure. So Weka is another one. I think a lot of folks like Vast. They have a lot of good reviews. I've never used either of them, so just what I've heard and people have told me. So I have no dog in this fight. But a thing that we definitely run into in training and problem with Lustre is the poor metadata and the small files. Even if you kind of beef up the number of metadata servers, it's still an issue. It's hard to work around it. A little chatty too, protocol-wise sometimes. And these two also support GPU Direct, which is the RDMA directly to the GPU. So you can RDMA directly to the HBM, and you can't do that with like Lustre. So lots of reasons to use some of these newer storage options.
So just quickly,
Yep.
Why would you have millions of files? I mean, is that from the data sets?
The data sets, yeah, that you're feeding in. Yeah.
You gotta train them all on all the pirated books.
Yes, exactly.
That you've cut and scanned
Yeah,
and.
5-minute increments of my website.
And none of that is not piracy, right? It's only when we do it.
Yeah, exactly.
It's innovation.
That was just the employees that took their computers home and did that. We're just reading it from their brother
They were doing it from the corporate network.
Oh.
Yeah.
It came out in court cases.
Yeah, yeah. So, some employees had some interesting quotes that were came up in that. Super briefly on software stack, I kind of already talked about it, right? There's hardware, the kernel, NVIDIA or ROCm, or the AMD equivalent, CUDA ROCm. I think everybody runs containers, and then you have user applications above it. I think we've kind of talked about everything else, using nickel instead of IBM, instead of MPI. Yeah, so even Slurm users now, so SCEDMD, which made Slurm, was spun off from Livermore, I believe. NVIDIA bought it. So now Slurm is owned basically by NVIDIA. And they also are supporting this thing called Slinky, which allows you to run Slurm on Kubernetes. And it's because some folks, they just like the interface of Slurm, right? They're used to submitting jobs. Like, I have a job, I want to run it. And so that's basically what this does. It maintains the same user interface, but it's doing Kubernetes, node pools and stuff and management on the back end. So that's interesting. And I'm starting to see it pop up. It's been around for a while, a few years at least, but I'm actually seeing people. And the other groups have similar solutions. CoreWeave, a NeoCloud, they have their kind of own Slinky-like product where they run everything on Kubernetes. And then if you want Slurm, they give it Slurm on top of Kubernetes, which to me is kind of weird, but I guess that's what people want. And if you look in the nodes, right, it's just regular old Linux. LSPCI, and there you go. There's the stuff.
Out of
Yeah.
curiosity, on the CUDA for NVIDIA and ROCm for AMD, this might be more of a software thing than a hardware thing, but have you seen anyone using AMD's HIP toolkit?
Yes.
Or
AMD engineers. No, I have. So I actually, yeah. So I've worked a little bit with AMD folks about trying to get folks to use it more, and so they definitely pitch it, and we've pitched customers to use it. And so I've tried it.
Would it actually allow them
Hipify
to-
stuff. That's what that's the verb.
They were all NVIDIA or all AMD, but would that actually allow them to do a mixture of NVIDIA and AMD GPUs? Because that's kind of what it does, right?
So HIP is a component in ROCm. It's a lot of different things. And for a little bit, they were actually employing the person who's developing Zluda, which was another translation layer. And that developer was very upset when AMD told them after many months of development that they couldn't legally release it. So
Yep.
they threw away all the code AMD paid for, went back to the previous version, got employed by Intel, and continued developing it.
Okay.
Yep.
So there's drama with it.
Yep.
Okay.
Yeah, but they were trying to get customers to use it to hipify things. Yeah. Thank you for. You remind me of so many things that have fallen out of my brain, and I thank you for it. I was like, oh yeah, I forgot about that drama.
So these things run batches. How long do these batches take? The 20
Oh,
seconds.
For these? Oh, this could be like the training job, right? So it runs for months. Well, it crashes eventually, but you have to worry about mean time before failure. But order days on really big jobs. Well, not really big. It depends on the scale. So you have an estimate of the mean time before failure, so before the time that the job will fail, and depending on the scale, it could be maybe minutes to hours to days.
So you run it and then you stop it and then you check to see that all the equipment's running and then you start it over again.
Yeah, basically, yeah. But a lot of it's automated. So right, there's things where you go through the logs, you look through the message or NVIDIA logs, and you can figure out what the issue is and remediate. There's warm spares available, so you can and there's ways to estimate if it's unlikely that you lose all of the, at worst case, you lose the last checkpoint to what you computed, right? And there's ways to estimate what the delta is there, and they do that because, right, we're only using FP4, right? Who cares? So there's lots of tricks. So because there's lots of resiliency and fault tolerance built in when you scale up, because there's lots of failures.
How often are they typically checkpoint?
It depends on, well, it really varies by the lab, I would say. They have different philosophies about how often to do it and their risk tolerance.
These data center level GPUs also run ECC, so they can use the error rate statistics to fault a GPU out.
Yeah, there's a lot of fancy labs do predictive analysis on just that, and even the bit error rates, like on NVLink, and you can start to see when there's going to be failures. But one of the big things is that, like, a lot of times the failures are like optics in the network, in the fabric. You'll get link flaps, and sometimes it could bring it down. But ByteDance had a really nice paper about how to monitor queue pairs in IB to kind of, to your point, to like see when the errors start to pile up. And like if you have a stalled queue pair, you can just go do something to reestablish that connection or reset it, and then you have. It seems like they had a higher uptime than other labs and a longer mean time before failure. So there's lots of research into this because it's expensive to crash.
Sensitivity to individual nodes.
Oh, for sure.
So
Yeah.
the whole, basically you have to.
Yeah, if you do it naively, right, you're running on 16K nodes, and when you get one XID error on one GPU, or it falls off the bus, and then all 16K are just sitting there idle until you reload the checkpoints, and then you start over again, right? So, yeah, you could do that if you like to burn money, but folks are generally incentivized not to, yeah.
So I kind of missed something. So the training versus the running queries.
Yeah.
So is this all training?
Both.
Okay.
Yeah, I'm actually going to talk about that.
Yes.
Right here. So, everyone always like one step ahead of the talk, right? So basically, like, so what are some of the workloads that folks are running? So generally, like, these are massive. So you do run these hero jobs and the training jobs. So that'll take up a large proportion of these clusters. I think the last estimate I've seen is like 60% of the cluster will use for these kind of training jobs. It's not just the hero jobs. You have to do lots of experimentation and understanding like what data mixture produces good models and so forth. But there's also post-training. Like RL is huge now. This is something like 40% of the budget now. So all of the RLHF and basically after you get a pre-trained model that like understands English and has some weird sense of things, but it doesn't work, right? It's not like a thing you can chat with, and so you have to teach it how to interact with humans and how to answer questions and so forth. And so that's where this fine-tuning comes in. And so folks are spending just more and more time on inference, and it's actually also leading to huge amounts of CPU usage now too, like millions and millions, if not tens of millions of cores for using RL. So you have all these GPUs, and then because the RL is blowing up, now you've got this huge increase in demand for CPUs too, which is kind of crazy.
Okay. RL.
Reinforcement learning, sorry. Yeah, thank you.
Thank you.
Yeah, so this is reinforcement learning. And then inference, right?
The difference is that you're training, all the other, the pre-training is sort of like random data. It's all the data, you just don't.
Yeah, it's totally, it's just like a fire hose of data, like, here you go, learn what you can, you know.
Learning is more procured.
Yes, yeah, it's like very specific, so it's like learning how to respond to, like, you know how like different agents have different personalities? That all comes from the reinforcement learning. And how to follow directions, and how to be a chatbot, and how to write code, and how to debug things. It's all this reinforcement, or how to follow its constitution if you're a model that has a constitution, right? It's all RL.
Creators' Twitter post.
I'm sure there's more than training that goes into that. Just like API calls probably too, and database lookups. And then, yeah, of course, inference. Inference is very different, but of course there's always inference. Inference is going through the roof because people are using models all over the place now. And that's very different than this. I have a roofline plot that will kind of show the difference in it. Actually, I'll show it to you right now. I don't know why I didn't put it either. So if you just look at a standard roofline model, are folks familiar with this kind of model? It shows a difference. So like here, you have arithmetic intensity. So if you load data into compute, how many times can you operate on that? The more you can operate on it, the better, because you're not sending data back and forth across the bus. and then performance, what's the teraflops. So when you're in this domain here, when you're memory bandwidth bound. And a lot of this is just like algorithm based, right? And there's some tweaking, of course, you can improve the algorithms to get it better, but this goes up, and then once you get to this ridge point, then you're compute bound. So training tends to be compute bound, because you load the data in there, you've optimized it, and you're just churning away on the data that you've loaded. But a lot of the inference has all of these different parts that are memory bandwidth bound, and so you get less efficiency. So the problems that you're solving for and optimizing for over here are quite a bit different than what you do for training. Kind of out of order there, but I just wanted to mention, so inference is a bit different just in terms of the computation needs. So one thing I just want to mention about like observability here, we've kind of touched on it a bit, but because it's so expensive to run these things and your workloads are so expensive, like observability is like critically important, right? I always use the 16K for some reason, because that's just like the magic number for it, that a certain class of models were trained on. So in my brain, it's kind of like burned, like that's what you train a model on, 16K. So you have all this stuff, like you need to monitor the GPUs for errors. NVLink has errors. The nodes, right, the standard stuff like DIMMs, CPUs, those have errors way less than GPU or IB. Those are pretty good. You do see them sometimes. Storage, right, storage has problems sometimes. And you also want to collect the logs. The logs are important both for predicting failure and also analyzing and understanding why the node failed and how you can recover from failures. And so you have to collect all of this telemetry all the time and try to automate recovery and understanding how your job is working and how well you're using the cluster all the time.
Isn't that what the second data center is for? Is to run the AI.
This is nothing for this stuff is nothing. Although, man, if you really crank up the resolution of the metrics, right, you can use a lot of storage, right? So people have to like kind of figure out like, oh, how much do I want to know versus like fill up all the storage that we have available. So it's a bit of a art.
You don't have the AI managing itself yet.
No, it'll do something bad. Okay, so just want to do a time check here. When do we get out of here? I've been talking for a while.
Typically around 9, like in about 15 minutes.
Okay.
We're kind of open-ended. if
Okay.
people are still-
Okay.
Yeah.
So I just kind of alluding to this, but like every workload has to deal with different things, right? So that's why I kind of put the this one up. This is kind of getting to the heart of the matter. Because these have to deal with different things, I don't really want to get into this too much, but so there's a thing called a KV cache. Getting into the weeds here maybe a little bit for this talk, but when transformer, part of the math involved in how transformers work is there's a bunch of matrix multiplications, and 2 of these matrices are the keys and values, and an optimization to save compute is you basically cache the keys and values, so these 2 matrices, and you save them, and then the next query comes around and you can reuse those. So this doesn't exist at all in training, so that's like a totally different thing. There's all kinds of tricks and techniques that folks are using to make inference faster because of this, because it's all memory bandwidth bound, and we haven't figured out how to get it up to be compute bound yet. Let's see if there's anything back here I want to kind of talk about in detail.
Why they're buying all the RAM right now?
Oh, well, for all the GPUs and the CPUs, right? It has it all. I kind of want to just skip through some things in case so we can leave some time at the end. Okay, so yeah, so basically, right, the whole point of this is like they're not just doing one hero run. There's a mix of workloads on there. And I just want to get to this so that we have time to ask questions. So where's it going, right? So the rack kilowatt was only 40 a few years ago, and the kilowatt are going up. Somebody mentioned, right, that we're going to 800 at some point, right? The next NVIDIA racks, the Kyber are 600 watts, but like 800 pieces of the infrastructure that support 800 are on their way. Definitely by the end of the decade, it'll be 800 for sure. 800 volts, not kilowatts. There's more and more optics getting involved in replacing copper. Another advantage of moving up to the higher voltages, you can smaller copper, so there's less copper. Disaggregated inference is a big thing. There's also disaggregated storage. You're just like breaking up partitioning all the different pieces in these. One thing that early on I said that I would talk about, but I skipped for now, is multi-DC training. So in these big clusters, the clusters are actually split up into multiple data centers, and they're networked together in a single fabric, right? And there's ideas, and people have played around with even using, so in a single site, there's multiple data centers, and they're networked together. But people have been saying, oh, we need even bigger clusters, and there's only so much power in a given place, so let's connect data centers that are across the continent or whatever. And so they're looking at ideas like erasure encoded RDMA, so to make sure you can do RDMA across this crazy WAN, right? Which is
How's the latency? Because one of the issues with RDMA.
so, yeah, I mean, you'd have to change the training, right? Because this would be training. You'd have to change the training so the syncs are infrequent and latency insensitive. Yeah, I mean, I don't know. I feel like people are going crazy. Like, are you ever going to actually do that? I don't know. But you know, and some more clusters. We've.
PowerPoint presentation. Here's our potential solution. We haven't tried it yet.
All right. That's it. So there's about 10 minutes left. So went through a lot. Happy to go back. Happy to open the floor to discussion. We had a lot of questions, but yeah.
I think there's like 2 or 3. In a few slides ago, you had mentioned there's the importance of CPU to GPU NVLink, right? Because they're using what is now Spark, and what was it used to be, the ARM CPU that they used to have. What is the importance of that? Because I thought it was really only the GPU to GPU NVLink. I totally understand that requirement. Why the CPU to GPU?
Like this guy?
There.
Yeah. Well, there is higher bandwidth, right, between memory bandwidth between the CPUs and the GPUs. So the memory loading is faster, right, from the NVMe through the CPU to the. So I mean, a lot of these optimizations are just motivated by memory bandwidth, basically, because it's always a bottleneck for any operations on a single node. And so any of these things you'll see are probably motivated by that.
But then wouldn't the underlying storage medium be the?
Yeah, it is.
Okay.
Yeah, the NVMEs are probably going to be, because they still have to go over PCI.
Right.
But they're actually closer to the GPUs because they're on, yeah. But yeah, I can't say for sure, but whenever I see stuff like that, it's like memory bandwidth, right?
Yeah. I'm just always curious, like, why does that, the CPU to GPU, it just doesn't, like, I don't rock it, obviously I'm not in the field, so.
I mean, there's also like vertical integration, right? Like they own everything. And there's also probably power implications, right? Just the power draw is going to be different than if you have 2 Intel Xeon chips on there as well, right? It's all on the same die. Well, it's not on the same die, but it's on the same board.
Those cores aren't even standard ARM intellectual property. NVIDIA is an architecture licensee, not an IP core licensee. So it's NVIDIA custom ARM cores inside there.
So what does the AMD equivalent of this look like in terms of the CPU?
They have, so
Are they doing
kind of
their own
interesting.
also?
Funny, where's the picture that I had? On Azure, the Azure version of this with the AMD GPUs actually has Intel CPUs, just like the NVIDIA ones. But so I don't know how they make, I can't speak, like I know Oracle also has them deployed, and I don't know if it's exactly like the way we have it on Azure or not, but it's a good question. I'd be curious. I always found that fascinating. But I know why they did it, right? So the nodes are between NVIDIA and AMD are basically the same, except for the GPUs are different.
Basically, the GPU then is loading almost as directly as it can from like an NVMe array of some kind, right?
Wait, say that again, please?
Is it that the GPU has the loaded data directly from like an NVMe array?
Yeah,
So that
both of them do.
means the CPU is there to manage all the PCIe links.
Yeah, absolutely.
So if
Yep.
you're having a flash array
45 seconds, as it's loading all the data from NVMe into memory, then all compute's done once the entire model weights are in memory.
Yeah, that's the pre-fill kind of stage. Yep.
Sorry.
Yeah, yeah.
Another question. I was trying to figure out like what is the cheapest way to do, obviously none of the training or the inference, et cetera, at home. I'm talking about just simply like for local LLM stuff. And it turns out the Volta, like the V100s, the SX7 2 and 3 ones are now hitting the eBays of the world. So they're like, for the 16 GB ones, they're like $100 a pop, etc. My question to you is, do you know what the like the deprecation cycle is for y'all? And which dumpster do you put these things into?
Where do I need to go stand?
Yeah.
Yeah. I know we still have T4s
Oh wow. Okay.
running,
Okay. Never
so
mind.
they have very long
Got it. Okay.
lifetimes, and they're used. When we deprecate clusters, like you basically have to like kick people off. You have to keep telling them it's going to be deprecated. Use these better, faster ones, and there are workloads there running. So it's kind of tough.
I see. Okay.
It's gonna be cheaper to heat your house.
Yeah, they're no longer CUDA, like I think CUDA 13 is supposed to be like the last or something.
They dropped driver support for it years ago.
Yeah, yeah. But I thought CUDA 13 just came out, right? I thought the
Pretty new, yeah.
V100 still
Yeah,
works
they
on.
did have a legacy branch there still
Yeah.
supported, that's why.
Okay, yeah. But my understanding is that's the last one. CUDA 13 is the last one for the Volta.
Ampere was the first generation that really allows you to do a lot of the stuff, so
Right.
it's gonna continue to be supported for a while, even once that hardware is dropped by the hyperscalers. You're gonna be competing with everyone else in the world to try to get it.
Totally. I mean,
Yeah.
like,
You already are.
Yeah, exactly, right? And it's like, I mean, the funny thing is, there's some automotive grade, the
Orion?
A100s,
Oh.
the Ampere. So there's what is it called, the
Jetson?
P199. I think
Oh,
they call it.
okay, yeah.
And it essentially doesn't have an NV link, so it's like a standalone kind of. There's like supposed rumors that it has the NV link hardware in it. They just removed the tracing for the interface itself or something. So I don't know. Anyway.
Dev kits.
Yeah, right. Exactly. And so people are talking about like removing the chip and putting it into a bare board from a broke blah blah. It would be pretty cool to run like the A100s, but that's like so costly. It's like $1,500, which is cheaper than like getting like a 5090 or whatever. But
Yeah. Well, I think like the Spark's expensive, right? The DGX Spark, but part of it is because of the interconnect it has in there, so that you can network them. But the new RTX look pretty. Yeah, those new RTX things that I bet those. I'm kind of curious about them. The new RTX like dev kit or whatever they're calling it, and the laptop I think, because they're Blackwell.
Yeah,
so
but
it could be pretty good.
DB10 but the issue is still though, it's using like the GDDR6 or something versus the
HBM.
NVMe,
Yep.
right? So even with the Volta, the memory bandwidth is at like 900
Yeah.
gigabytes per second,
Yeah.
and of course the NVLink is 300. But with the other ones, it's like it's still like it's like a third of the bandwidth or something.
Yeah.
So, I mean, it's and of course like the cost, right? Like if I get with a V100, I can essentially get a 128 gigabit thing for around like $2,500 ish. Like it doesn't handle. There's no CPU or RAM, etc. included in that. I already have like a cluster of random parts sitting around, so I can just plug it into.
Got a basement full of home lab stuff.
I do. But it's like I have a case cluster right now.
Yeah.
No, so I can just plug it into one. But still, like those DB10s, I think are like $5,000 something.
Yeah, they're crazy.
I don't know, something like that. Don't quote something.
Yeah.
For what it's worth,
Consider
the
running
RTX
a book.
Spark, I'm waiting to see an actual decapping of it, but the rumors were that it's just a process short GDDR6 It sounds better.
That's exactly what I imagine. Without the interconnect
Yeah,
circuitry.
single die,
Yep.
two dies on the back.
Yeah, so I'm pretty interested to see what that looks like.
And I think they did a process shrink of the GPU side because the CPU on GB10 was using 3 nanometer supposedly, and
Mhm.
the GPU was 4 nanometer.
Oh, I didn't know that.
3 nanometer now because it's the same die.
Just
Oh, that's
put it
interesting.
On Amazon for $5,000, maybe they haven't, you can see.
Little microcast. But I do have to say though, like the networking side of things, I mean, obviously it is the thing of like that, it's, like the GPU itself has that network connection, right? Like to the HCA or whatever speed, right? Like, but the Mellanox, like the yield, before NVIDIA bought it, the Mellanox switches and interface cards that do InfiniBand, they're on the used market for pretty cheap. I mean, like, it's like if I remember, it's the NDRs. There's no XDRs, which is why I was super surprised
Yeah.
that you said. But that's like still like for a Switch, it's like under $500 ish.
That's surprising to me. I mean, well, geez, time's weird, but like 8 years ago, like InfiniBand stuff even used was still pretty expensive. So I'm surprised you can get NDR for the Switch at that point. That's cool. Do I want to? Makes me curious.
200 gigabit switches or 100 gigabit, you can get things for somewhat reasonable
Yeah.
prices. The 50 gigabit and below is comparatively cheap.
The
Yeah.
56 gigabit, the InfiniBand, the 56 gigabits per second one is like $100. You can literally get like a 36 port, what is it, Mellanox 6036 or something. That's like $100.
Wow.
It's super cheap, the 56 gigabits. And that also does the 40 GPE Ethernet that has the multi.
It also consumes as much power as one of your inference machines.
It's actually.
How we doing?
It's
What do you think?
actually not that bad.
The
Like
gas
you can tune
turbines
it down.
fast.
Sorry,
Yeah.
I won't go
Well,
into
I
the
just
specifics.
want to be mindful of time
Yeah,
here.
exactly.
Any less? Yeah.
Yeah, so a few slides back, you kind of had like that little circle of like, oh yeah, this is the.
This guy. Yeah.
Yeah, right.
Yeah, this guy.
That the AI companies are like going through. So like as an expert in like this field, like, you know, nothing is infinitely scalable as much as Jensen Huang wants us.
Yeah.
When does that stop? Like how close are we to the point where, you know, like Moore's law, you know, kicked in and, you know, things stop scaling? You know, same thing here eventually, you would think, right?
I mean, all bubbles got to burst, right? And
When they start charging for it?
yeah, who knows? I mean, it's gone on longer than I thought, and the models have improved way more than I thought they would initially. So I have no idea. I'm constantly surprised at how things keep improving. I think that's what I would say. It's like
You might think that they're
every
gonna
few
outdate
months.
it, but they never do.
Yeah, every few months I'm surprised by something a model can do.
For the last 3 or so years, it was expected that 2027 or 2028, we were going to hit a wall from a hardware side, but the models have improved at least 30-fold over what we expected to have in 2027, 2028.
Yeah.
And we keep finding new funny tricks like reducing precision.
Yeah.
FP2.
Well, look up one bit models. Yes, that's what I was going to say. There are 1-bit models. I've never looked in detail because I just looked at it and I was like, nope. So, yeah. All right. I had a lot of fun. Any final questions? I would thank everyone. Yeah.
Well, this is kind of summarizing what everybody's saying, but it's an accounting question. You know, so what is the depreciation if you build a data center, you know, your latest data center? How many years before it's completely obsolete, and how does? I mean, we've sort of been talking about that, but
They don't appreciate, they're appreciating. They really do.
You rent
That's
it
right.
out.
You know? I don't know. I'm not a finance guy, so I can't say.
But the question is about, you know, how fast is the hardware becoming obsolete? Because it's the hardware. I mean, the other stuff, you know, you can.
Yeah. Well, folks are still using really old GPUs for stuff.
Okay.
So it's still utilized. All of the, it's not like there's spare hardware, spare GPUs laying around not being used that they would save electricity on. It's all used.
Is it maybe less expensive computationally the model after it's initially created.
Oh, for sure.
So basically, they probably could have a pipeline where they create the new model initially with the high-end systems, but over time, if it's like, okay, this model does its thing, they can run it on older hardware.
Yeah. I mean, there's lots of efforts to do that kind of thing. Like downloading Gemini at home, that's super capable, right? Imagine thinking that 2 or 3 years ago, or when ChatGPT came out, that you could just download a model that's way better than ChatGPT, and it runs on your local machine. That's crazy.
My question is more of a general like supercomputing question. Like, let's say, like you mentioned that like Azure like offers like supercomputing like technique. Like, what are some good resources to like learn more about like Slurm and like how to actually build things properly to like run on like a supercomputer?
Yeah, so I think just like standard, so a couple of things. So like parallel algorithms, like I had like parallel algorithms, and like I learned like MPI and OpenMP, these like classic like distributed training things. Like those kinds of resources, like now you don't even need to buy the books, right? I'm old enough that I had to buy the books because this stuff didn't actually exist on the internet. But so like looking up those kinds of things. The fundamentals about how you use distributed systems, the distributed algorithms, and like I said, like the AI clusters are just like the old HPC ones, right? It's the same stuff. You just kind of change it a little bit for your new use case. So distributed systems, parallel algorithms, CUDA stuff, all the CUDA stuff you can just download from NVIDIA for free and learn like from the API and the examples. Their code is freely available, and they have tons of examples for all kinds of different domains about how to do stuff. There's some classic textbooks for like CUDA, what's it called? Programming Massively Parallel Programs. It's like a classic textbook. It's how I first learned CUDA, like in the no, it wasn't the 1900s. I can't use that one. I can't use that one, but a long time ago. Yeah, so lots of resources. So yeah, that's what I would stick to the tried and true algorithms and classics, and they'll get you a lot of the way there. And in fact, you'll be in better shape than a lot of folks working in this space now because they don't know that stuff. Cool.
Awesome. Thank you.
Thank you. It's a pleasure.